and gentlemen, thank you very much for coming out on this wintry evening to attend the third in our annual series of July lectures in physics. I've been asked also to make a couple of announcements. Next week there'll be a talk by Hans Bachel, who's a distinguished physicist from ANU, who will address us on various aspects of emerging areas of physics, and particular laser physics. This evening we have Andrew Peele, who's going to discuss aspects of synchrotron science. I've also been asked to announce a university public lecture by Ada Yonat, who's Nobel laureate in chemistry, who will discuss chemical basis of life processes revealed in X-ray crystallography, which is a subject I discussed last week. That will be on Wednesday, the 13th of August, in the Copeland Theatre in Berkeley Street in the University of Melbourne. But today it's my great pleasure, my great personal pleasure, to introduce Andrew Peele. Andrew and I have known one another for the best part of 10 years. Andrew is unique amongst my colleagues in having a background in the law and rowing. He spent a great deal of his undergraduate years doing both, I understand. Fortunately, he saw the light, and having both studied the law and practiced the law, he came back to physics. He did a PhD with Keith Nugent, who's a distinguished X-ray physicist and now Deputy Vice Chancellor at La Trobe University. Andrew postdoced in NASA and worked on some novel optical system, the so-called lobster eye telescope, which was never actually launched, but introduced a lot of very interesting and innovative optical systems in X-ray physics. He was recruited by La Trobe University and worked his way up the ranks there to the rank of professor, and was ultimately poached by the Australian Synchroton when Keith Nugent moved on as director, and now Andrew is himself the director of the Australian Synchroton in Clayton, which I would like to point out to the audience is resolutely not at Monash. The topic of tonight's talk is the Australian Synchrotron. So it's a major public investment. It has had a colourful history, but it makes very significant contributions to scientific life in Australia and to the prestige of Melbourne as a centre of scientific research. And Andrew will today tell us about the Australian Synchrotron and you, and us. How an MCG-sized microscope is adding value to our lives. Ladies and gentlemen, Professor Andrew Peele.
Very much, Harry, for those kind words. And before I really get going, I have two product disclosures to make. I'll try and get this fixed on so it doesn't chafe too much. The first product disclosure is that I'm under some significant pressure this evening because my mother-in-law is in the audience. So I'm really having to perform tonight, so otherwise I may not have a home to go to. The second disclosure has to do with the word MCG in the title, and I'll come to that one in a second. But really what I want to talk about tonight is what I think is one of the most significant investments in scientific infrastructure that's ever been made in this country. And why that's important, why it's important for everybody. But along the way, I hope we'll manage to have a little bit of fun as well. And indeed, I'll even throw in, I think, one equation, a little bit of physics. I'll make some apology for that, but also talk about what it can do. The question I get asked the most after having explained to people what the synchrotron is no, but what really is the synchrotron? What is it really? What does it do? So I'll try and answer that question as well. But really, the synchrotron has now been going for about 7 years, and it's amassed a wonderful track record in outcomes in scientific discovery and in finding new ways of doing things that affects all of us. So that's why that bit's in big font. And then around about 11:30 tonight, I'll get onto a bit of a soapbox at the end about why this sort of investment's important. So, if you zoomed into the heart of the synchrotron, this is one of the sorts of things that you would see. You see a lot of stainless steel. For those who've been around a bit, you might recognise these as electromagnets. You'll see a lot of concrete, you'll see pipes going hither and yon, and these are the tools of the trade. These are the parts that make the synchrotron work, and the X-ray beams that the synchrotron generates goes out in pipes like these down into the facility itself, which as you can see is prodigiously large, and runs, so that pipe would be coming out of that, inside that concrete area there, and runs down what we call beam lines, which is where we do our experiments, and I'll explain a lot more about that as we go on. If you zoom out a little further, what you'll see is a big round building. You'll see a number of other buildings which make this place really tick. And in fact, one of the things that's really interesting about a synchrotron facility is when you come to this place to do experiments, they can take anywhere from a few hours to a week. And when you're working a week, 24/7 round the clock, you come with a team of people and you want somewhere to sleep at night. So there is in fact a guest house on site for degree scientists to trudge across this little section and catch a few hours of sleep. You'll also see one of those beam lines. Most of them are contained in this building, but one of them is special, runs out through a tunnel into this exterior building, and I'll show you some reasons why we've built that one in that way as well. So that's what it looks like. But now I come to my second disclosure, which is it really as big as the MCG? So this is a question that's very easily answered. If you go onto Google Earth, you can get a picture of the MCG, and on the same scale you can get a picture of the Australian Synchroton. So no, it's not quite the size of the MCG. It is about the diameter of the playing field. And there are many of these types of facilities around the world, and some of them are bigger than the MCG. This is a synchrotron facility in Grenoble in France, and is a couple of kilometres around the outside of the ring. And in fact, if you go around the world, there are, of this sort of class of facility, there's a couple of dozen dotted around the world, of the Australian synchrotron size or bigger, that run what we call a user program, where researchers apply for time and come through from external institutions to do experiments at the facility. In fact, there's probably around about 60 synchrotron facilities per se around the world, most of them being research tools in university departments and others. You can also see that we're one of only 2 such facilities in the Southern Hemisphere, and we're the best one in the Southern Hemisphere. So, what is the Australian Synchroton? We've discovered it's a big round building, but let's delve a little deeper, and this is where I'm going to inflict a little bit of physics on you, and really try and come to grips with what are these facilities and how do they work. So, to do that, I'm going to have to go back in time a little to Michael Faraday, who is the physicist. Michael Faraday, in fact, is a personal hero of mine because I was scared of mathematics. And so, among some of my colleagues who are like Harry, who is less scared of mathematics, we experimental physicists always feel a little bit like second-class citizens. But we can always point to Michael Faraday and show that without superb experimental physicists like him, and he spent a good 5 decades or so meticulously doing research and documenting that research. Without people like him, you wouldn't have the underpinnings of electromagnetism, you wouldn't have the underpinnings of special relativity, you wouldn't therefore have had Einstein's, you wouldn't have then gone into the whole 20th century explosion of physics that we had. So Michael Faraday, in fact, was a chemist to start with. He was adopted by the Royal Institute, Sir Humphrey Davy of the Royal Institute, and he's given a job there where he started doing research on a whole host of things, but among them electricity and magnetism. But he was also a really good communicator, and he started what's known as the Christmas Lectures, a famous institution that started in 1825, which is a series of public lectures, not unlike this series of public lectures. In fact, I believe that the July lectures in physics here are in some ways founded on the Christmas lectures by the Royal Institution. In fact, they're so famous now that they're annually telecast, I think by BBC 15 or something like that, but you can find them. Now, in those lectures that he gave, and he gave 19 of those Christmas lectures, there's a really famous one called The Chemical History of a Candle. And for those of us who like to give public lectures in physics, where you do demonstrations and the like, this is a salutary lesson to read this little textbook, because it has all of the tricks of the trade that professional presenters of physics use and have used for well over a couple of hundred years. It has things like all of the standard demonstrations to do with atmospheric pressure. Many of you may have seen the one where you put a little can on top of the stove with a bit of water, boil up some steam, put the lid on, and then let the thing cool down. There's a couple of ways you can do that. One is you can let it cool down by itself, go off and give you a lecture, and then 10 or 15 minutes later the thing will actually just crumple as the steam condenses and the air pressure on the can collapses the can. Michael Faraday did that demonstration repeatedly. So at the end of his lecture, first lecture, he he was doing obviously a lecture on the candle, looking at things like flames. He also gives us a lesson which I probably won't listen to, but he realised at the end of the first lecture that he spent far too long looking at pretty pictures and doing demonstrations and not talking enough about the philosophy of the thing. So I suspect I may fall into Michael Faraday's trap in that area because we've got a lot of really good things to look at here, but hopefully we'll get across some of the underlying philosophy of the thing as we go on. So what Faraday did in all of those years of looking at electricity and magnetism was he started to formulate this great idea that he called lines of force, which was this understanding of how, when you have a charge, how it affects space around that charge, or a current indeed. And in fact, this experiment is one where you take a charged area, the black dot in the middle, suspend a whole lot of fine threads of material in oil, and the electric field coming from that charge will induce the threads to align along the lines of the electric field lines coming from that charge. Basically, it shows you how forces interact when you put a field, another charge into the area around the central one. Now, this idea about fields is tremendously useful for telling people how other things will interact if you put them into the vicinity of another charge. And indeed, that whole field is incredibly sophisticated now, and you have automatic molecular calculations where this is a water molecule in proximity of, I think it's an alcohol molecule or something, but you can see these little cones that represent the field lines coming from the distribution of electron charge around these molecules and how they disturb the space around them and give you an idea of then how these things will interact as you move them around. So fields are a really useful concept, but Faraday went a little further and realised that in fact you can think of fields as entities in their own right, and in fact that fields are real things in some way and are a property of space. And in fact, when you start to generalise in this way, you realise that you can have fields that exist in their own right, in some way separated from the charges that created them. And I'll show you a little bit about that in a second. But firstly, in order to honour Faraday, I thought I'd just show you a quick demonstration. Now, what I have here is, if you look on this screen, is a little cathode ray tube. And this is a Melbourne University public lecture, so I suspect many of us are of the vintage where we remember what a cathode ray tube is. It's the part that used to sit in the back of television sets before they became this thick. And it's a very simple device where you heat a filament and then apply an electric field which then will effectively drag the electrons out of the filament, accelerate them across the intervening space. And the electrons that are doing that in this case are running up against this phosphor screen and illuminating the phosphor screen. So far, so good. In fact, this is a simple model for how we start a synchrotron. We start with a bunch of electrons, which we generate in this way, and we accelerate them in a similar way. But the trick is with the synchrotron, when you saw those magnets, what we need to do is guide those electrons around and get them to do what we want. And indeed, it was Maxwell, it was Faraday thinking about fields that then allowed people like Maxwell and Lorentz to understand how a moving charged particle in a magnetic field, what the force law that governed that interaction was. And so I've got here a simple bar magnet, and what you'll see is that when I put the magnetic field into the space where the electrons are travelling, those moving electrons travelling through the magnetic field will experience a force. So as I bring the North Pole up, you'll see that as it comes up, the magnetic field lines are pointing in this direction. It causes the electrons to describe a radial path. I'll stop waving it around so much. A radial path and bend in that field. If I reverse the polarity of my magnet, they will bend in the other direction. So all of those colourful magnets I showed you in the first slide are doing exactly that. They're applying a magnetic field to a travelling beam of electrons and causing them to go around corners. So that's how we control that beam of electrons. But there's something else fabulous that happens when you accelerate a charged particle. And this is really one of the great insights that came from Faraday's thinking and that Maxwell then took on. And in fact, I thought I'd go back and honour this lecture series because this is actually from the first year of the July lectures, given in 1968 by Professor Jeff Opat, who was a professor of physics here at the School of Physics. This was the third lecture of that year, I think. And he spoke in that lecture about Faraday's laws of induction, Maxwell's laws, and then how you go from that to describing how you generate light. Now, and in this picture, what we have is a picture that looks like that one I showed you with the threads emanating out from the charged particle. There's a charged particle, these are the field lines emanating out from the charged particle. And now the question is, what happens if I take that charged particle and accelerate it forward? So I've accelerated it briefly, and then after a period of acceleration, I'm now moving the charged particle slowly forward. So you can see that these lines out here are the original lines from the stationary particle. These lines in here are the field lines from the moving particle, and in between, during that period of acceleration, you get a kink. And that kink, as time goes on, travels out. And in some ways, you can think of that kink of now being divorced from this particle and this kink of electric field lines travelling out in space. And in fact, that is what light is. Those kinks are in some ways representative of what beams of light or photons of light or waves of light are travelling through space. Let me now turn to the wonders of computer simulations to see if I can make that a little bit more real. This is a little package that was put together. There's my charge with the field lines running out from it. And now I will make that charge describe a trajectory. And now what you can see is the charge running around my racetrack, and if I pause it at the right stage, you can see that my charge here has the field lines of a constantly moving charge. But what I've got is the kink due to the acceleration around the corner here. So when I put it in my magnetic field and caused it to bend around the corner, what happened was it threw off a whole bunch of kinks or wavefronts, which are now manifesting themselves as their own independent packet of electromagnetic radiation. So this is light travelling out due to the acceleration of this charged particle. So this is the basic process that we use in a synchrotron. Bang, as it just goes around the corner there. What we have is those magnets in the straight. The electrons come up, they bend through the magnet, and they throw off this beam, which we then take off in a pipe. And that beam is the beam of light that we generate at a synchrotron and do the experiments with. So, fairly simple set of events, but there's a couple of other steps that we have to bring in as well. So let's just look at that in diagrammatic form. Here's our electrons coming through what we call now a bending magnet. Terribly exciting names that physicists give to these things sometimes. It will go through the magnet bend, and you'll spray light outside. Another way of thinking this is it's conservation of momentum. You've changed the momentum of the electron, you need to generate something else with momentum to balance out the momentum loss. And that's a beam of light that comes out here. Now, you can get a little bit trickier than that, and of course we always go beyond and beyond. Instead of just having a north-south pole magnet, you can put a whole bunch of them and cause the electron to bend repeatedly. And if you do it just right, with all of those repeated bends, you can get the beams of light that come out on each bend to add up together. This is called an insertion device, and you can generate much more powerful beams of X-rays by using this additive trick. So, there's another question we have to ask though, because when I send my electrons through that little chicane of magnets, the magnets are a few centimetres apart. So you would expect the wiggles in the wave field that come out to be a few centimetres apart. But what we generate in the synchrotron are X-rays, which have wavelengths of around about an angstrom, or 1/10 of 1/billionth of a metre. And these are about 100th of a metre. How do they get so short? This is where special relativity comes in, because we've accelerated our electrons to such a point that they're now travelling at the speed of light, or so close to the speed of light that it doesn't matter. So, we get to invoke Einstein, and we know from special relativity that a very fast-moving object will perceive something as length compressed. So these magnets, which were 2 centimetres apart, will now appear to be, and if we do our mathematics and we know the energy of this electron, we can work out the scaling laws, they will now appear to be about 3.7 microns apart. Now that doesn't get us all the way there, it gets us about halfway there. There's another trick as well. If you've ever heard of the ambulance siren as it departs, the well-known Doppler effect, well, these guys are emitting waves as they're going through this process, and they're moving very quickly. So we'll get a blue shift, we'll get a Doppler shift, which is the relativistic Doppler shift that happens as well. So we get the length compression and the Doppler shift, and the two of them together combine so that the light beams that are now spraying out from this accelerated electrons are of the order of X-ray wavelengths, order of a nanometre or 1/10 of a nanometre in scale. So, we've now gone through the mechanics of making our X-ray beams. One final effect, another great plus that you get from special relativity, is that the special relativity effect compresses what would otherwise be a spherical wave travelling out and causes that to another type variation of the contraction effect, causes that spherical wave to become compressed into a beam. So now this bunch of light that comes out from an electron going around a corner is now a very short wavelength, very powerful beam of X-rays. And this is what makes synchrotron such a powerful tool. The other great thing about that light is that it covers a broad band of spectrum. So we in fact do get visible light out from the synchrotron, but we're optimising for X-rays. But we can choose the energy of our X-rays in our experiments. So they're all the bits and pieces and the components. So now, let me bring the full majesty of the resources of the Victorian State Government and the Federal Government to show you in exquisite, three-dimensional, animated, rendered detail how a synchrotron works. So as you can see, in the vegetable synchrotron, we have a cherry tomato. It comes out of our little electron gun here, and it's accelerated through an electric field. It's actually, by this point, it's travelling at pretty much the speed of light. We then put it through what's called a linear accelerator, where we use some tricks of radio frequency waves to push them down the linear accelerator into this round string beam object, which is in fact the synchrotron. It's called the booster synchrotron, and it's a series of magnets in a circular racetrack and has one radio frequency cavity. What happens is you get the electrons, which at this point are now travelling, well, they're travelling at the speed of light, they have an energy of 100 MeV. As you put more energy into, as you accelerate the electrons, rather than them getting faster, because they can't go faster than the speed of light, they gain energy. And at this point they have 100 MeV of energy. Don't worry about the numbers, but basically we want to get them up to 3 billion electron volts, 3 GeV, to optimise our process. The RF cavity here has the effect, if anybody's ever made their kid throw up on a merry-go-round, it's the same effect. You basically, as they're going around this racetrack, the RF cavity is in sync, hence synchrotron, with the electron beam, and it basically accelerates it, taps it each time they go around, and puts more and more energy in each time. In about half a second, that process of ramping up the electron energy is complete, and the electron beam is then taken from our synchrotron track and injected into the storage room. which is where we then put it through our Bagel bending magnets to create the light bursts that we need. Now, before I go on though, you might think, well, this is an incredibly complicated process, but in fact, it occurs in nature as well. In fact, only recently has it been discovered that the Van Allen radiation belts, which is an area of high radiation around the Earth, have a lot of charged particles, electrons, and there is a low frequency radio frequency wave that emanates as part of this system with the Earth, which is coherent with this travelling beam of electrons and acts exactly the way a synchrotron does. And it accelerates the electrons in the Van Allen radiation belt up to the speed of light. In fact, it's long been a mystery where some of the sources of high energy charged particles come from. And this synchrotron process is now thought to be one of the components that create high energy particles that then go on and impact through the magnetic field lines of the Earth and create the wonderful aurora and so on. So these processes are real in nature as well as real in the synchrotron. Now, the last step, injected into the storage ring. We call it the storage ring because the idea is to keep the electrons travelling around this ring as long as possible. And of course, as you go around the band magnets, you get the, for those of you who may have missed that, I'll just play it again because it's so fantastic. You of course get your sprays of pasta travelling down these pipes, which are our beams of light that we can now go and do experiments with. And in fact, there's one final step. These were our bending magnets. I mentioned our insertion devices. And of course, with the insertion device, you get much more pasta. That's really what we want. And of course, when you do this, it works. In fact, at the Australian Synchroton, when we built this system, this is a plot that I grabbed off our screen monitors this afternoon. This red line is the current. And you can see it's got this zigzaggy shape. Because what happens when you put your electrons into the storage ring, as they shoot light outside, they lose energy. And you put that energy back in with another RF cavity which taps them along. But every now and again, one of your electrons will bang into a stray molecule that's sitting in your vacuum. You can make your vacuum as good as you like. There are always going to be stray molecules or stray atoms floating around. You'll occasionally have a collision with your electrons and lose your electrons. Your current will decay. To offset that, what we do is every couple of minutes, we inject a little pulse more of electrons to keep our current topped up. And this, it's hard to see the axis here, but this oscillation here is, the current here is 200.3 milliamps. This oscillation is a little less than a quarter of a milliamp. So the current is maintained to much better than 1% uniformity. And that then means that as that beam goes around, it's generating the same amount of light each time it goes down a beam pipe. So our light source is incredibly stable. Another thing to point out is all of these green things. These are each of the beam lines, each of the different pipes that takes that light off onto a separate experiment. So let me now start to talk about some of the things that happen there. So what is the Australian Synchrotron really? Yes, it's an electromagnetic particle accelerator that uses special relativity and quantum electrodynamics. But what it really is, it's a bumping great light source. It creates a really powerful beam of X-rays that have wonderful properties. They're pulsed, there's timing effects, because every time you're getting the electron bunch going past, and they go past every nanosecond or so, you get a burst of light. For most experiments, that just feels like a constant source of light. But if you're doing something really fast, you can use that as a timing effect, that little stroboscopic effect. It has a continuous spectrum of light, which means you can choose your energy, and I'll show you why that's useful. It's collimated, it's a beam, which means that you can direct it as you wish. It's polarised, that comes into play, and it's brilliant. Brilliant is a key word for meaning lots of it. If you put too much in the beam, you will melt things. And that's actually really handy, because in fact, most of what you do with the beam line is you throw most of that light away. And you throw it away so that the bit you have left is the perfect light for your experiment. Okay, what can you do with it? You can take images. This is a rat. This one was not alive, but in principle they can be alive so that you can do longitudinal studies. You can do what you can do at a hospital and do a CT scan and pull out the bone structure. But what you can do at a synchrotron is pull out the soft tissue structure as well. So you can see in this rat the lung structure. Or you can pull out the lung virtually from the three-dimensional model, or you can pull out the heart, which you can do in exquisite detail. Now, groups doing this sort of imaging are able to image the lung structure dynamically. So they can watch an animal breathing in 3 dimensions in the lung. And that group that was doing that work, actually we started off doing that work before the Australian Synchroton was built. And they're now doing the work at the Australian Synchroton. We're able, as a result, to understand the process of how you put air into a preterm baby. So the simple way is preterm baby having trouble breathing, whack on an oxygen mask, crank up the pressure and blow some air in. Of course, that's really bad because the lung tissue is very, very sensitive. And if you crank up the pressure too much, you're going to tear the lung. But the downside is you need to get oxygen to the brain as quickly as you can. So you need to clear the fluid out of the lung as quickly as you can. What they were able to show directly by imaging is that instead of blowing in an overpressure of air, you rely on the muscles in the baby and you make it breathe out. And you breathe out against an overpressure. In short, you put a straw in its mouth, put the straw in a glass of water and give it a squeeze. And that blows out the air, blows out the fluid, and it's the quickest way of getting air back into the lungs. As a result, the World Health Organization protocols for how you put air into preterm babies were changed. So my opening sentence, saving lives, has already been demonstrated by research done at the facility. It's faster because you can take this stuff dynamically. You can do this 3-dimensional imaging dynamically. You can only do that with the synchrotron because that's the only place you have enough X-rays to put through the system quickly enough to do that imaging. What else can you do? You can look at molecular bonds. You can look at the state of molecules in organic substances. So molecules are really interesting things when they get organic and they start to flop and they stretch and they do all sorts of interesting things. And you can, as a function of energy, pull out characteristic curves that show you the state of those molecules. It's a great way to fingerprint the state of molecules in a system. If you do that in the lab, you've got noise sources to contend with, and you don't know if some of these things are real or if they're noise because you just don't have enough light. When you look at the synchrotron spectrum, you can see that things like this are in fact real, and that helps you fingerprint the state of the molecules to a much better degree, so you have much more sensitivity. You can do beautiful things. You can take a small spot of X-rays, shine it onto what in this case is a grain of barley. And when you shine a beam of X-rays onto a sample, the sample will fluoresce. It excites the electrons in the elements in the object, and then they will relax and give off light at an energy that's characteristic of the atoms that's in the material. And so from that, you can then work out how much, in this case, iron, manganese and zinc there is in your object, and you can do a false colour map based on concentrations of the constituents that you're interested in. In this case, what they're interested in is looking at wheat, in fact a grain sample, and understanding how to get micronutrients into the kernel. When you process a grain sample, we all know that the good stuff in rice, for instance, is in the husk. If you're eating white rice, you're not eating the stuff that's healthy for you. And what you want to be able to do is process the thing, keep it healthy for you, and have something that people want. And in fact, again, coming back to the World Health Organization, one of the major killers due to malnutrition is not lack of calories in the third world, in children. It's actually lack of micronutrients. And over-processing or incorrect processing of food is a big contributor to that. So if you can breed staple crops where they survive the processing step and still deliver the micronutrients, you've done a huge service to mankind. So in this work, this is researchers at University of Adelaide in South Australia, were able to modify strains of rice so that there is uptake in iron. So the bright points here are showing iron concentration in wild type and modified rice, and showing an increase in the uptake of iron in those crops, and in fact succeeding. And so this work is now going to field trials where they're now starting to plant these in the real world and being able to see if they can get them onto market. So another fantastic result. I mentioned energy. Now, if you can tune your energy you can probe your sample at different energies, and you can scan your energy and get measures of your sample at different energies. Now, I'm not going to go into the detail here, but what this team was doing was looking at a catalyst for the process of oxidising water to generate hydrogen, for the hydrogen economy. Now, if you can do that in an energy efficient way, and do that with a catalyst that it doesn't get used up in that process, that's reversible, then you've actually done something very useful. And they were able to probe the chemistry of this experiment because of the fact that they could tune the energy from the synchrotron source. And in fact, that work was groundbreaking in the sense that they were able to demonstrate that particular manganese compound was actually very useful for this process. Now, it is the International Year of Crystallography, and if you'd been at the July lecture last Friday, you would have seen Harry Quiney telling us about crystallography. Synchrotron facilities are the workhorses of crystallography around the world. Almost all of the protein structures that are now discovered are discovered at synchrotron sources. And the basic process is this. First, make a crystal. That's often the hard part. It can take 20 years to figure out how to purify and express a particular protein, and then get something that absolutely does not want to turn into crystals to turn into a crystal. Proteins that really like flopping around in water and in solution and interacting, they do not like becoming rigid and forming many repeat copies of themselves, which is what a crystal is. But if you can overcome that step, make a crystal, put it into a holding device, shine the X-ray beam onto that crystal, then what will happen is a wonderful effect of X-ray physics, or effect of physics, called diffraction, and light will come off in a series of beams from that crystal. And this spot pattern can then be reconstructed and turned into a depiction of what the protein structure is. And protein structures can be fantastically complicated. Thousands and thousands of individual atoms, many interesting ways of depicting them that can be shown. But once you have that, then you can understand the electron density of this, you can understand the field coming out from this object, and go right back to that picture I showed you with the field interactions of different particles. And then you can model how that protein interacts with other proteins and other constituents around it. As I said, this is the workhorse of synchrotrons. It's one of the biggest areas of work that gets done in these facilities. But the hard part is that first step, the crystallization step. What happens if you can't crystallize? Well, you can put your protein into solution and shine an X-ray beam on it, but you don't get this lovely spot pattern coming out. You get a much more complicated looking diffraction pattern, but you can use that information to get back what's called shape information, using what's called small angle X-ray scattering in solution, and that sort of information gives you something that looks like this. Now, it doesn't have the same exquisite atomic level detail that crystallography does, but it gives you the envelope, and very often it's all about the handshakes. It's how the molecules tuck into each other and how they talk to each other that's important. So this sort of information can also be extremely useful. And again, this type of beamline is another one that gets a really good working out from structural biology. So, we now know how to make synchrotrons work. We now know what their capabilities are. What is a synchrotron? Well, a synchrotron is in fact none of all of those things I've talked about. A synchrotron is a place where researchers can go and probe whatever their field of interest is. It's a suite of laboratories that lets you do just about everything. And in the remaining time, we'll go through some of these effects. But first, a little bit of history. As I said, the synchrotron's 7 years old. It was announced in 2001. These things cost a lot of money. Ours is a mid-scale facility. Building the ring and the building is $157 million. Building the 9 beamlines that we have was another $50 million. And extending that long beamline that I showed you and making some of the other infrastructure around the place was another roughly $50 million. So there's north of $250 million of capital invested in the place. They cost a lot to run, cost around about $25 to $30 million a year to keep going. About half of that is actually people. The electricity bill's not insubstantial, that's a couple of $1 million a year. Now, what do you get for all of that money if you run it right? Well, hopefully I'll be able to show you some of that. The way the facility now works is that we're now operated through the Australian Nuclear Science and Technology Organisation, ANSTO. Why is that important? It's important because organisations like ANSTO have decades of experience of running scientific infrastructure in Australia. As many of you may know, ANSTO runs the only nuclear reactor in Australia, which is in fact a research reactor at Lucas Heights in Sydney. The interesting thing is, while that research reactor does things like making radiopharmaceuticals, irradiating silicon for the electronics industry, it also has a hall with a number of beamlines. And it takes neutrons out from the nuclear reactor and puts neutrons onto experiments. And neutrons are a wonderful tool for doing complementary research with X-rays. So there's a really great match for how you do research on materials. Just another thing I'll point out, the current funding for the Australian Synchroton is complicated. We have an emergency package that was put together a couple of years ago to see us through until 2016. It covers every research active organisation just about in this field in Australia and New Zealand, along with most of the major funding bodies, ANSTO and CSIRO. The problem with having a really complicated funding scenario is we now have to satisfy all of these masters in terms of access to the facility. Now, it is managed in a way that is very good in that most of the access is on merit. You have to actually have a good proposal to get access to the facility. But we do have to balance these funding components, and that does have a slight distorting effect on types of experiments you may want to run in a facility. Having said that, most of the beam time is given free of charge to these funding partners, and it's done on peer review system of proposals. This graph, these are all of the different beam lines, which I won't go into. The dark blue graphs show you how much time people are requesting. The light blue graphs show you how much time we can give running 24/7. So we're turning away about half the people that want to use the facility. Now that sounds terrible, and in fact it's actually worse than that because it's self-regulating. People don't put in proposals because they know how competitive it is in the first place. So the demand, the actual demand is even greater than what I'm showing here. But what this does do is allows us to select for excellence. And what you find is that the people using the place and the experiments that they're doing are incredibly good. They're incredibly good at what they're doing, and also they're working on really important topics. The throughput is prodigious. We're now through more than 4,000 registered users in the facility. And the great thing is that about half of those users are early career researchers. So they're PhD students, early career postdocs. So basically, we're training the next generation of scientists and researchers in the country. So let me give you a mental framework for how we actually provide value before I finally get on and show you some of the stuff we do. So I mentioned early career researchers. We have over 2,000 PhDs and postdoc researchers who've been trained in the facility. Also staff, technical staff, with some of the most advanced controls, mechanical and electrical control systems in the country. So we're training up a skilled cohort there. So the funding that you put in terms of training basically pays itself back immediately before you even start talking about interactions with industry, with company research, and interactions with more discovery-based research. But these are really where the bread and butter is. In terms of just raw outputs, again, what the place has been able to do is something almost unique. This is not a cumulative graph. This is, in fact, the number of referee publications coming out every year. And you can see that the number has been growing amazingly since we opened. I say amazingly because since this point, we've only had 9 beamlines. We've had the same 9 beamlines. We've had the same 24 hours in every day. So there's nothing that's changed in terms of our physical capacity to be able to do work, but our efficiency of turning experiments into outcomes has been going up. And there's a multitude of effects here. One is our staff is incredible, working around the clock, putting in systems into place and optimising people's research. Researchers are getting better at knowing how to use the place. We're putting in place things like supercomputing facilities to take raw data and turn it into outputs in real time as you're doing your experiment. So this curve is still going up. I keep saying every year, this has got to flatten out at some point, but it hasn't yet. The other great thing is I mentioned excellence. The measure by which many academics look at themselves is the sorts of papers and the citations they get on their papers. The sorts of papers we're getting into and the coverage we're getting is at the top of the line. We're getting the coverage in the Natures, in the Science, in the Cells, in all of those papers that recognise the best quality work that goes on in the country. Okay, let me talk about it. There are many types of research that's done. As I mentioned, structural biology is one of the workhorses. There's this notion of a value chain that you'll often hear governments talking about going from discovery-based research to proof of principle research to market development to mature interactions. The great thing about Synchrotron is it works at all levels along this value chain, and it works across an incredibly broad array of disciplines. Here's an example of discovery space. Insulin, as we all know, is the chemical that we use to help regulate diabetes. The structure of insulin was discovered many years ago, and in fact was an incredibly important discovery at the time. But one of the holy grails since then has been, how does insulin, which is this little molecule here, how does insulin interact with its receptor? How does that protein shake hands with the protein that's sitting on the cell and then signal, and then that handshake signals the cell to let the glucose pathways activate? This docking mechanism has never been able to be understood. So people have never understood what is the optimal form of insulin. We know insulin that works, but we don't know which bits of the insulin molecule you can leave off, and the process will still work. So in this work, what the group was able to do, and they started trying to crystallise this complex of insulin shaking hands with its receptor in 1991. And that work then went through to basically 2012, when they were able to do the research, 2012, 2013, and get it published. And the reason why they were able to get it published is because they were able to finally get some crystals. And they were very small and crappy crystals, which is a technical phrase, and put those crystals in the beam, get those diffraction patterns, use all of the in-house computational resources that they had to put this handshake back together, and then be able to sort of conceptually understand. So this is the receptor, this is the insulin floating around in solution. There are movies of this that's generated as well. The receptor will dock, that will send a signal through the receptor into the cell pathway that then allows the glucose pathways to activate. Now, what that lets you do now in future is now you can understand which bits of the insulin you need, which bits you don't. You could design a better insulin. If you're in a third world country where you may not have access to good refrigeration resources, you could design an insulin that doesn't need refrigeration. And again, that would be a huge change. Let's move along the value chain a little bit. We all know about zinc. We all put it on our noses and various other bits of our anatomy to help protect us from the sun's rays. The Cancer Council has been very strong on slip, slap, slop and sending messages about using zinc. There have from time to time been residual concerns about using what's called zinc nanoparticles in sunscreens. This is formulations of zinc which are at the nanoscale. The reason why manufacturers like them is because they go into creams nicely and they rub in nicely and become invisible. But of course, one of the questions is, what is the interaction of nanoparticles with the body? And there was some work done a couple of years ago by CSIRO where they looked at how much, in fact, this was basically the experiment, they rubbed in the zinc onto people's skin and then they analysed their blood to see how much, if any, zinc nanoparticles were getting into the bloodstream. Good news was basically none at all, but there are still mechanisms where zinc nanoparticles can get into the bloodstream. For instance, if you have a cut or a scratch or an abrasion. So the question then is, can the body deal with zinc nanoparticles in the bloodstream? So this experiment was fantastic. What it did was it exposed human cell macrophages, which are the dustbins, or the dustbin people of the human body. They basically hoover around and soak up and attack things that shouldn't be in the body. They exposed those macrophages to concentrations of zinc nanoparticles, and then using an object called a focused ion beam, they were able to ablate away layers of the macrophage then used the synchrotron to do this fluorescence mapping experiment and map out concentrations of zinc at different depths in the macrophage. So then they were able to show as a result that what was happening was that the macrophages were in fact ingesting the zinc nanoparticles, which is great because it means they're removing them from the body. But even better, they were able to show that the oxidation state of those nanoparticles was changing and moving into a form that's known to be not harmful to the human body. So this is a fantastic piece of research that the Cancer Council rightly jumped on and started putting out press releases about, that show that even if you're getting zinc nanoparticles into the body, then we know that the body's own defence mechanism is in fact able to deal with them. And not only that, able to deal with them at actually incredibly high levels. In fact, levels that are so high that they're known to be toxic. It would be very difficult to get that amount of zinc into the body in the first place. So at this level, this is a great result, obviously, if you're making zinc sunscreen. Let's look further down the value chain. Hospira is a company which nobody will have heard of. They are an employer of 650 people in Victoria, another couple of hundred people around Australia. They export nearly $300 million of generic injectable drugs. Now, the generic drug market's a really interesting one. What generic manufacturers do is they look for drugs as they come out of patent, and they make those drugs in ways that are as cheap as possible. And in order to get them onto the market, they have to show the regulator that the drug that they made has the same effect and is the same drug as the one that was under patent. So Hospira came to us and said, we want to make some of these generic drugs, and we want to show FDA in America that the thing that we made is exactly the same thing as the one that everybody's been using for years. And we were able to work with them and generate those reports to show, using some pretty high-tech imagery and spectroscopy, that in fact their drugs were the same. The report went to FDA, came back without a single query or objection. Hospira's been around for 99 years. They said that had never happened, ever, in their history before. So by using the right tools, you can actually help business move forward. And for them, that's really important because it shaves time off getting the drug onto the market. A generic drug has a shelf life of about 3 years, where it's profitable. If they can get onto market at 3 months earlier, they've got a huge advantage over their competitors. This is basically looking at the over 200 companies that we've done work with at the Synchrotron and looking at the sector breakdown. You can see, as I said, it's incredibly broad. And let me try and give you some context on that. The areas of research that we do are, largely speaking, medical and life sciences. That's things like the structural biology work, materials science, and the everything else. Really, it's multidisciplinary sciences. It's where you bring together physics, chemistry, biology, mathematics, engineering, and do things that you couldn't otherwise do, very often looking at earth and environmental systems or energy systems. Those underpin research in just about every area you care to think of, and these are, in fact, I went to the website and looked at all of the portfolios of government. These are all of the portfolios of government, bar two because I couldn't fit them into my PowerPoint template. And when you look at those, we have outcomes in all of those, the net result of which leads you towards either economic outputs or better well-being in society. And as I said, behind every one of these, you can find a story, whether it's, let's look at an example. Let's look at the transport system. Transport system on rail carries about 5% of Australia's GDP. Tracks, particularly ore tracks, carrying tracks, get a huge amount of punishment. And in fact, rarely fail gracefully. When a track fails, you get a mess, and these sorts of messes cost millions of dollars in the best case, and in the worst case, they cost lives. So what you want to be able to do is understand your rail technology, and in particular, understand the welds in your steel, and understand the effect of other metals in your steel. In this case, what you're looking at is manganese, and you can zoom in using the synchrotron. A bit surprising perhaps when you think of nanoscale sort of research that's often done on the synchrotron, putting in a thumping great railway track, but you can, and you can generate these sorts of maps, which show some really interesting effects where manganese is confined into these sorts of vertical striations. Now what this is giving the researchers is a tool to be able to understand and model the effect, and then link that back to fatigue and strength in the railway tracks. Now, if you were doing this using an electron microscope, the way you would do it, you would get that sort of information, but you would sample it by going bang, 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 and you get a bunch of points like that. Here, you're getting a density of information that allows you to build up a full picture in your railway track. You can look at this another way. This is basically the same picture. This is basically saying, go from discovery space research in whatever area you like, look at how that comes out with impact, and then argue that it provides either benefits to people's pocket or benefits to people's well-being. Now, I promised myself I'd have a couple of minutes to do this. I'm going to show you at least two things before I get onto the soapbox and finish. One, I'm going to show you just because it's beautiful, not because it's going to make anybody any money. This is Degas' portrait of a lady. It's in the National Gallery of Victoria. And you can see there's something going on. See this dark mottled area underneath? And in fact, it was known that he'd reused this canvas. Now, the state of the art here would be to take that picture and take it to an X-ray machine, like at a hospital, or take it to an infrared machine. And in fact, this is the infrared image. Now, you can just see the outline. There's definitely an outline there. If I turn it upside down and zoom in, lips, nose, chin. There's somebody else underneath in this painting. So now what are you going to do? Well, we take our X-ray beam, zap each spot point by point, measure the fluorescence spectra coming out, map the elements at each point, know what the pigment in the overlayer was, subtract the overlayer out, look at the layer underneath, identify the pigments, and put the false colour back in. Sounds easy, right? It took these guys 2.5 years to do this, but this is what they got. So you can strip the virtually, you don't have to physically do this, you can virtually strip the top painting off and reveal the portrait of a younger person underneath. This is in fact identified as one of the models that Degas had used quite frequently. So now the National Gallery of Victoria's got a quandary because the painting underneath, you might argue, is nicer. So then what do you do? So of course what you do is you use this and generate some posters, and then you get the best of both worlds. You can also do things like this experiment. There's a problem with sheep. This is actually research done by a New Zealand group, and I'm not going to go there any further. But what they were looking at was this problem with sheep hides. When you kill a sheep, typically what happens is you throw the skin away. The strength in sheep leather is not sufficient to stand up to making things like shoes. You can make Ugg boots out of them, but that's about it. But if you can find a way to strengthen that sheep leather, you've now got a plentiful source of leather. So what the group did was that they said, well, can we understand the microstructure of the leather and then use that in a feedback loop to find what sort of processing steps we can do to strengthen the sheep leather. And when you shine an X-ray beam onto the skin of the sheep, this is the sort of data. I'll just sort of show you what the data looks like. This is what's called a small angle X-ray scattering image. These rings give you information about the size of the fibrils in the leather and in the skin, and also the orientation of those fibres. So now you've got a tool that tells you how big they are, how far apart they are, and what direction they're pointing. And you can link that to the strength. So when you do that, you can then try different tricks in the processing step, go back and look at it, another trick, no, go back and look at it, and you can iterate on that. And to cut a long story short, what they were able to do was double the strength of that leather. And as a result, that adds around about $10 a hide to the value of a sheep. Multiply that up by the number of sheep hides that are thrown away, and that's about $100 million to the Australian sheep industry. This group from New Zealand are frantically patenting everything they can think of to do with this process, and then rolling out into a startup company at the moment. Now, we're not going to run out of time, but I'll throw one open to an audience challenge, because what I like to say is that we do research on just about everything. So if one person can throw out a topic that they're interested in, I'll attempt to link it back to something that we do at the facility. So I've got one volunteer to just pick a topic, any topic. So tough. All right, environment's an easy one. Okay, this group, cement is actually really interesting. When you cure cement, it emits a prodigious amount of CO2. The chemical reaction that goes on in cement emits a huge amount of CO2. The question is, can you use other materials as constituents into the cement? It has two useful functions. One is, if you use this so-called biopolymers, in Russia I think they call this earth cement, but basically it's waste and landfill. If you use these biopolymers, can you use those as a useful constituent of cement? And what's the effect of that on the strength of the cement? And what's the effect of that on how much CO2 is emitted? So this group is able to do that and show, firstly, that the microstructure of the cement is not affected in a material way, and in fact that the structural properties of the cement are perfectly adequate for construction tasks. And secondly, that the chemical reactions that go on are much, much more beneficial, and you reduce the CO2 production by an enormous factor. So the company that's involved here has had several research grants, but is now a viable company that actually markets this thing called Ecrete and sells that. And then as a result of some of this research, Vic Roads changed some of the standards required to allow this cement to be used in footpaths and other construction. So a great outcome for the environment. Now, I'm afraid I am going to run out of time, so I could go on and do every single one of these, and I would love to, but I am going to get onto the soapbox for just 2 minutes to finish up. Because what I want to talk about is, why should we continue to support a facility that's cost the country $200 million and cost the country around about $30 million every year? Well, apart from the fact that there have been 20,000 researchers using the facility, 4,000 individual users, but 20,000 researcher visits use the facility in 7 years. Apart from the fact that there's now over 1,500 refereed papers generated by the facility, apart from the fact that it saved lives, apart from the fact that we're interacting with over 200 companies to generate results like the ones I've shown you, there is another argument, if they're not good enough, there is another argument which says this is infrastructure. You don't ask the end users, you don't ask companies to pay for the national highway system. That's essential infrastructure for the country. That's the sort of thing that government should be funding. The Synchrotron is a national superhighway for science. It's the place that allows researchers to take their samples and drive them to outcomes that let them discover things that they can't do in any other way. All the work at the Synchrotron that's done has to pass a test that says, do you need to use a Synchrotron? If you can do it in the lab, we'll send you off and do it in the lab. But if you have to use the Synchrotron, this is where you have to go. Before the Australian Synchroton was built, a tiny fraction of the sorts of synchrotron outcomes that you saw here were achieved every year by scientists going overseas. And speaking as one of those who spent 20 years doing suitcase science, this is the better way to go. It's incredibly fast. All of those structural biology results that I showed you cannot be achieved by making samples in Australia, shipping them overseas and doing the research. 2 reasons. One is a lot of the time they get destroyed in that process. Secondly, the duty cycle, the time elapsed in going backwards and forwards, means that they can't refine their experiment until they get to their answer. In fact, if you talk to many of the researchers who got these results, they'll go on camera and say, we would never have got these results if it wasn't for the Australian Synchroton. And in fact, the Australian Synchroton is a big part of the reason why structural biology is incredibly strong in Australia, and particularly in Melbourne. You can also look at the National Commission of Audit recommendations, and that talks about sort of criteria that the government expects to see before it funds infrastructure. There has to be clear national benefit. Hopefully I've argued a little bit for some of that tonight. It also has to be not feasible for the private sector to fund it. So again, same argument. Private sector doesn't fund roads. Why would it fund a $200 million facility? In fact, you can go to private industry, and these are drug companies working in Australia, will quite happily say, we benefited from the facility. We don't have the capacity to put on an R&D department. So we need the Australian Synchrotron researchers, we need the university researchers to partner with at that facility to get these outcomes. And similarly, Hexamer is a great company. They work on developing antifungal resistant crop strains. And they've done a huge amount of work demonstrating new varieties that can withstand this. But even they will say, if you're an investor, this sort of investor, it's great to use the facility, but the level of investment is not such that you can support that with the private sector. If you look overseas, you see that this is exactly what happens at facilities overseas. So those couple of dozen facilities overseas are all government centrally funded. They will all work with industry like we do, but that level of direct industry interaction where they pay for the access is a few percent of the operating costs. You bring in a couple of $1 million a year. Where the real benefit is in these discoveries, where you go from that serendipitous discovery that you can identify submicron specks of gold in waste dirt to a method for prospecting for gold by looking for gold in gum leaves, which now means you've got several million drill sites all around the country without having to do an environmental impact statement. So, but nobody would have ever invested in that. Last point, again, if you go through reviews that have been done on these facilities overseas, and we are a bit player in terms of investing in these sorts of facilities. If you go to South Korea, they have a synchrotron that's bigger than ours, and they also have the next generation of synchrotron, which is about a $1 billion investment in a device that lets you do more of that sort of structural biology work. If you go to Japan, they have a bigger facility. If you go to Taiwan, they have a bigger facility. So these tiger Asian countries recognise the value of investment in this sort of infrastructure. Similarly in America, the responsibility for design, construction and maintenance of these facilities is uniformly through a central agency, not through 52 different institutions, each of whom have their own funding agreement KPIs that fund the facility currently. So our argument is that it needs to on-go in that way. And finally, how do we do this? Well, how do we do this is by demonstrating the outcomes, demonstrating that we're providing world-leading results, demonstrating the national benefit, demonstrating that we're partnering with organisations like ANSTO that allow us to leverage that experience over the years, and then take the ownership of the facility from the state government, and the state government has said that they want to do this, move the facility into the national sphere. I didn't show you these numbers, but more than half of the researchers coming to the facility are coming from outside Victoria. So it's truly a national facility. It's not a Victorian plaything, it's a national research institution. So to do that, you need to move the asset into the Commonwealth. You need to provide a long-term operating funding solution. And again, that comes with the asset transfer. And you need to continue building beam lines. We have 9. A mature facility would have 30 or 50 beam lines around the ring. My last bit of soapbox. This is my own invented metric. It's the number of beam lines that your country has per $1 trillion of GDP. Australia has 9 beam lines and a $1.5 trillion GDP, giving it a ratio of 6. Canada, almost the same country, almost the same GDP, has twice as many beam lines as us in its facility. Incidentally, we generate twice as many publications as Canada. So we're actually 4 times as effective as Canada. I hope there's no Canadians in your view. Diamond Light Source is the UK facility. 24 beam lines, $2.4 trillion GDP, about twice as many beam lines per dollar of GDP. It goes on. The issue is that we're undercapitalised. We've spent $250 million building the framework. Beam lines cost around $10 million each to continue building out this sort of capability. Every time you do that, you add new capability, new types of science, new types of research, new types of industry that you can interact with and generate more outcomes for the country. So my last point is then the way that you convince the people with the money of this is by engagement and by communications. We have a long and fruitful collaboration with state and federal governments, but in fact it also comes down to you, and this is part of the you in my title. If you're at all convinced by any of this, then we all have a responsibility for saying, why is science important? Why are the outcomes of science research important? Why do university researchers, academic researchers, industry researchers spend so much of their time poring over computer screens, trying to get data out? It's because generally they're convinced of the fact that what they're doing is important. It will change people's lives, and it will develop new ways for businesses to operate, for doctors to operate, for curators in museums to operate. And in fact, if we didn't believe that, then I suspect none of us would be here in the first place. But it's important to keep that message alive and to remind politicians, local councillors, anybody in decision-making capacities, that this sort of endeavour is probably one of the most important things that we can be doing as a country. And at that point on the soapbox, I will finish. Thank you very much.
I'm sure that Andrew will be happy to answer a couple of questions.
Yeah, appreciate that. Thank you so much. We have it all here. For science. We need this. We're more important. But that we are very how much new science and technology help us? Somebody have mental program, genetic program, emotional program, or what the relationship between mind and brain, and what the relationship, how matter create mind and mind create matter. How can help us? Thank you.
That's a brilliant question. So the whole interaction of, well, health, not only health but also mind and brain. There's a huge amount of work that actually is happening. Going fairly prosaically to start with, things like Alzheimer's disease. There's a lot of interaction between metals and proteins that people think are relevant for Alzheimer's. Synchrotrons are fantastic for looking at metals in proteins. And so there's, in fact, I won't, but I'll show you many pictures where you can scan through and you can identify the presence of different metals and how they interact with cells, and different conditions can change that interaction. So that's part of the answer to that question. You can also look at neurons directly, and you can look at the interaction of them. You can look at the way signalling changes in different environments. So again, there's many practical things that you can do in that space.
I'd rather see that rock free funding go to the Synchrotron funding. On the your cars and motorbikes from the past, the faster the vehicle goes, its line changes around the curve. The faster it goes, the closer the radius. So the practical accelerating the Synchrotron behave the same way. And question number two, when you're looking at imagery of organic material, either grain or a rat, where is the animal or the organic matter placed as a being?
Okay. So first question, those bunches of magnets that I showed you, we colour code our magnets. The yellow ones are bend magnets. They're the ones that make the bend go like that. There are also green ones and red ones. What happens when the electrons go around that bend is there are what are called chromatic effects. So the different energy electrons spread out in different ways. So I'll describe different radii, and your bunch of electrons will spread out. Our green magnets and our red magnets refocus the bunch. So the effects you're talking about are there, but we have magnets to correct them. So it refocuses them back. I forgot what the second question. I completely forgot what the second question was.
Where does the organic matter?
Thanks. It's really simple. Basically, what you have are those pipes that I showed you. You throw most of the light away. It will come out typically out of what's called an exit window, which is usually a window made of beryllium. The light will be travelling in vacuum through the pipe, pass through the beryllium into the air in the lab. And in some cases, it's really simple. It could just look like a tabletop with a stage on it, with a holder. And you put your sample in there. The crystallography ones that I showed you, basically they're a little goniometer, angle manipulating stage with a needle on it effectively. And that loop that had the crystal sits on the end of the needle, and the X-ray beam just literally shoots straight through it. The rat sits on a bigger chamber. They have little holders that the rats sit on. They often sit in little tubes that are sitting on top of their stages. Again, the beam is coming through the air and onto the sample. One thing you have to note though is all of those high energy X-ray beams, the X-ray dose is dangerous. The way you run an experiment is you go into what's called a hutch. It's a lead-lined building. You set up your experiment, and then there's a complicated search procedure with various interlocks that you have to go through to allow you to exit the building, shut the door, and enable the shutters on the X-ray beam. So it's almost impossible to find yourself in the chamber with the X-rays. But then you can leave, for instance, a rat or a sample in there.
significant debate?
It's just an observation, really. We could have had 6 more synchrotrons than what we spent on Mikey.
Yeah, there are many things in government. I say that if we have 1% of that, we'd have a new synchrotron.
It's obviously ultimately an instrument of analysis, but are there any processes which, say in modern electronics or advanced materials, that can they still exist without it somehow? Could you still do them, or do you have to have the data from the synchrotron to be able to do the processes over there?
Sure. I mean, look, people are infinitely creative, and there's often ways that, year 1 you have to have a synchrotron to do it. Year 2 you figure out another way to do it. And in fact, that's part of the raison d'etre of a synchrotron, is understand the fundamentals and the basics, and then work out how to take it out of the synchrotron. Work out how to do it in a lab or in some other simple process. And in fact, what I thought you were going to ask is, in terms of electronics, there is actually work directly being done on electronics as well, where people are investigating diamond materials as a substitute for silicon. As you make your electronics smaller and smaller, the heat loads of the currents flowing through your circuitry gets greater and greater, and you eventually melt your electronics. Diamond has a much greater tolerance for heat. If you can make your electronics out of diamond-like materials, you can then move into the next generation of electronics.
The latest of I'll have 2 more questions.
You were saying you need more beams. I don't even have more beams at the same time. What's the maximum number of beams?
My favourite question. As you go around, there are 14 sections in the synchrotron. That's basically 14 sections you can put an insertion device in, and at the end of each section there's a bend magnet. Each bend magnet can take a beam of X-rays, and each straight section can take a bend. There's a couple that get used up for other purposes, like the RF cavities. It comes down to 36 nominally. It would be impossible for us to build 36 beam lines just because of the real estate. The floor space isn't there. A number in the 20s would be a great number. The place would be chock-a-block and cheap at twice the price.
You have a priority, what would be the priority for electric?
So we've had a really extensive period of consultation where we went to industry and we went to researchers and said, what are the capability gaps and where is the demand? And we built up what's called a science case 2, where we identified 10 beam lines that should be the next cabs off the rank. Since then, we've developed up the conceptual designs for seven of those beam lines. And the one that would be first off the rank, it varies. In fact, it varies by who comes along with the biggest checkbook. But all else being equal, there are big capability gaps in what's called hard energy X-ray physics. So that steel work is difficult to do with our facility because the energy of the X-rays needs to be very high to penetrate. So we would like to make a more purpose-built beam line with higher energy X-rays that could do that sort of work. So that would probably be one of them. Another one would be more capability in the life sciences.
Last question.
In the early days, you studiously avoided 2 words. One was nuclear, radiation, and the other one was X-rays. How hard was it to team up with ANSTO?
Yeah, there's some really great public relations stuff around particular words, and nuclear is an interesting one because of its history. We're not a nuclear facility. In fact, for us, we're not a radiation facility either. In fact, the trick with us is keeping the X-rays going. If anything goes wrong, X-ray beam goes off, because that process of making the electron beam, guiding it through the magnets, guiding it through your insertion devices, sending it down the beam pipes, is incredibly complicated. The storage ring, where we keep the magnets and the electron beam circulating, we telemeter about 10,000 different things to keep that beam stable. If somebody crashes a truck on Blackburn Road and drives into a telegraph pole, there'll be a little spike in the electricity supply that comes into the place. And in the old days, that would have sent us down. Now, what we've done now is we've put in what's called an uninterruptible power supply, which is 3 3-ton flywheels with a spinning at about 10,000 RPM. And the kinetic energy in those flywheels allows us to ride out small interruptions in the power supply. So we're not a radiation facility either. When you turn it off, there's no radioactivity. The X-rays are only on when it's on and the electron beams are being accelerated. And yes, X-rays are an ionising radiation as well, and that's why we have the hutches and we have the interlock systems. But in many ways we have a huge advantage over someone with like a nuclear reactor. You can't, we can certainly throw the switch and walk away. Obviously, if you've got radioactive materials, you can't do that. So for us, it's very easy.